Try to understand. Or something, sometimes periodic, or you can say uniform. Okay. But it is, the point is that this is ideal. Okay. Now, what do you mean by non-ideal? Non-ideal thing is that see, I am doing the sometimes we say this is a non-ideal. Sometimes we say this is a natural sampling. A natural sampling means that generally what you are multiplying this xt with some pulse trend xpt, and xpt you are assuming I have a Dirac delta pulse trend. Then you will not get Dirac delta. What you will get? You will some sort of a very thin pulse, maybe like this. Okay. So with some pulse with some TP or so. Okay. Now in the Dirac delta case, TP tends to 0. Okay. Now in this natural sampling, but XPT you can do some sort of a Fourier series analysis where Cn equal to e to power j. This is my Fourier series synthesis equation. Okay. Now if I have an SF, the sample spectra means actually I am multiplying the things. Means in the frequency domain, what I am doing the collinear system. But we can, but this is my XPT. So that is what is my XST? XST equal to XT and XPT. That is, say you can multiply here XT, and finally when you take the XSF, the Fourier transform. That means you are taking the Fourier transform of this xt and e to the power j, this one. And what is the meaning of this thing? That means Fourier transform of these two multiplication means basically actually convolution of the individual spectra. In these spectra's convolution is x of f and e to the power j to pi 2 n pi fs means actually it is kind of a line spectra you are getting with Cn number of multiplication. Okay. So it is like that. So if I just do this thing, then if I do the convolution, it will be that means in the frequency, actually it is in the frequency domain impulse kind. Okay. Because e to the power j 2 pi nfs, what is the frequency response? Frequency response at c at fs, 2fs, 3fs with Cn kind. So if I just do this thing, if I just XSF, then actually Cn will be Cn into x of f minus f. This is the shifting theorem. If you remember that it is a shifting theorem. Now, finally, if I show the picture wise, just wait. So if you see the picture, say this is my xt, some band limited signal with f and fm. This is my band limited signal. Bandwidth is minus fm to plus fm. That means 2 into fm is my bandwidth. Bandwidth is 2 into fm, which is finite. Now I am just multiplying instead of pulses, Dirac delta pulses, I am multiplying with some XPT. XPT synthesis equation is Cn e to the power j 2 pi fns. If I just take the Fourier transform of this one, then what will happen? That means this is my f. At fs point, I will get all these pulses at fs, 2fs, minus fs, like that. Minus 2. Now, if I do these things, then actually if you just calculate this one, it will be looking like a sinc type of pulses. Okay, sinc means sin x by x type of pulses. So, where actually that you will get some C0, C1, C2, actually C minus 1, C minus 2. Okay. Now, I think you have studied these things in 6 signet. Is it not? Have you studied this thing? That means if I have a periodic pulses and if I know this amplitude, If it is 1 and if TS is known, so can you calculate this Fourier series? Hello? Can you calculate this Fourier series if that pulses and pulse train is given? Like Fourier series C0, C1, all these terms?
Yes, sir.
Okay. So I can calculate this C0, C1, C2, and actually if you just interpolate, you will find that it will be like this thing. And please try to understand that when you're basically when you're this T, this with T, if this tends to 0, what will happen? Actually, say this envelope, actually this envelope will be when T with like this, first it will be, then finally it will be like this, then finally it will be flat kind of. And when this flat means C0 equal to C1 equal to C2 equal to minus C1 equal to minus C2, like this. That means it's a pulse train kind of thing. Okay, that in the periodic ideal sampling you are talking about. We are talking about when TS tending to 0. So finally you see that what I will get in the previous case, what I have got all these TP terms. This width was, this is my TP was 0. Now here TP is finite, so I am getting my, in this position you will find this one. This little the effect of amplitude of xt, amplitude variation, that will come into place, which was absent in the previous case because that was some sort of a point sampling. And if you do the convolution of this one, this x with xf to xpf, this is f. Finally, that what will happen? That means ideally you had all flat kind of baseband pulses, baseband windows. Now you will have the main pulses will be the highest strength, and the little bit out of band pulses, little bit shifted pulses will be of lesser energy. Okay, finally, if I have fs greater than equal, if fs equal to 2 fm, I can do some sort of a filter so that I can cut it out. Okay. Now the problem is that if I have fs equal to 2 fm, then fs greater than 2 fm, then what will happen? Usually this one will start from this is fm, this is, say this is fs. Okay, then against this fs this will come. Okay, so about fs, about the 2fs, the next window will come, and depending on the strength of this waveform, that will be the strength, like this. Okay, so this is about the sampling theorem, about this frequency shifting property of the Fourier transform. Now that I told that actually this one is this, actually you are seeing only the main pulses, that this is basically this dotted line. This is basically a sink. If you see, this is a sink kind of thing. Okay, and if you see the Cn is 1 by Ts sink in Ts by Ts. Actually Ts tends to 0. You will find that it is all Cns are with equal amplitude. Anyway, so finally I have xst equal to xt and this one, which finally if you just do that, I mean spectrum wise, if you calculate the Fourier transform of xt and Cn e to the power j2 pi 20s, and finally I might have Cn equal to that for the discrete case, if it is Ts tends to 0, it will be like. So Cn will be 1 by Ts. Therefore, in the limit that x, I mean for two position, they are same for all in right. Now, so the basic point is that if I have a band limited signal, if I do the sampling, uniform or ideal, whatever it is, this basic that frequency response of the continuous time band limited signal will be replicated around the sampling frequency. This is the basic message. Okay. Now, if I have some sort of ideal pulses, then it's fine. If I have some sort of actual type of pulses, then we have some problem. But if Fs is greater than equal to F2Fm, then I don't have any aliasing problem. Otherwise, I will have aliasing problem. Okay. This is the basic moral of the story. Okay. So now I will. So this they are talking about aliasing actually. That means if your this is your Fs and see if this Fm maybe is less than 2 Fm or this thing. So generally in this case your Fs and Fs greater than 2 Fm, so I don't have any problem. So I can do a filter cutoff if is the form line. So I can generate the filter in this range, whatever it is. But if it is now, if it is, and actually what is the sampling? So signal aliasing means aliasing subna in this range means that means if you sample it at lower rate, what will happen in the sinusoid? Say I have my actual signal is this one. Say my actual signal is this one. Okay. Now I am sampling at this point, maybe at this point, okay, and at this point. Okay. So this is the uniform kind of thing, and I am doing ideal sampling. Okay. So sampling instant. Okay. Now in this sampling instant, what will happen? That means, but you can reconstruct a low frequency sinusoid in this one. Okay. So that means the signal at alias. So that means you could not reconstruct it properly. So that means what you have to do, you have to sample it with denser way. That means you have to sample the signal with right number of points. That depends on the frequency of the signal. That's why that we say that Fs is greater than equal to, it must be. Okay, then you don't have this type of aliasing problem. Otherwise, you will see that low frequency terms will come into picture. Okay. Anyway, so please study these things that regarding the sampling, what it is. Well, most probably you have already studied it, but it is always better that if you study it again. Okay. Now. Now, so that means we have understood that for if you can remember that in my previous lecture I was just talking. So that means when it is an analog information, I have first block is the sample that we are talking about, that sampling, but you have to do the sampling in that if it's greater than equal to 2f. Okay. It is in hertz. Okay. Now the next is that it is a quantize. So quantization you have most probably you have already studied this thing. So now let us see, and for quantize, so that means for quantization, you will have some problem. Okay, some problem in terms of SNR. Let us discuss that. Okay. Means it is, let us, this is page number, please note it down, page number 78. Say I have a signal. Say I am just drawing it here. Now, for a, say I have a signal, say which is, say like this. Now, say I am sampling it at this instant, and my quantization level is this one. Hey, this is my quantization level. This is another quantization level. Say this is another. Say I am doing some sort of a, say I have, and also I have a 4, means say 2 beats I like to transfer. Means in that 2 beat I am doing 2 quantization. So that means when I am sampling at this point, so my quantized value is this. When I am sampling at this point, but what will happen? That means I will basically take this value. When I will sample at this point, what I will do? I will basically take this particular value. Okay, rather I take the red one. So for this one, I don't have anything. Okay. And please assume that these are all uniform. I am talking about uniform quantization. Okay. Now, say my signal, again it is coming like this. Again, I am sampling at this point. So, which is, again, I will take this is the value. Then again, I will sample it here. I will just take this. So that means you see that at each point when I am sampling, so this is my error. This is my error. Say this is my error. Say here maybe error is minimum. Say you have started from 0, so error is 0. But generally I have an error. Okay. Now what do we do? So now let us check. So is that clear? That means I have some error and I like to characterize this error. Okay, so for due to quantization. Now say I have a signal which is say this is my, say, overall signals dynamic range. Dynamic range means say my V peak to peak. Please see, it is V peak to peak. Okay. Say for sinusoid it is 2 V peak actually. Say if it is some sort of a 1 volt sinusoid, or rather A sin omega t. V peak to peak is A sin omega t. What is the V peak to peak?
Sir, 2A.
So that means I have to take care of the whole range. Say I have some sort of a, say in this case I have taken 2 levels and I am assuming that this one is a sinusoid but only one side I have. So and I said that I have 4 different levels. So here it is, I am taking, no, I have L levels. Okay. Now L levels means that whole V peak to peak, this one is some sort of a L level. Now that means this is V peak to peak, this is minus Vp and this is plus Vp. Okay. Now each quantization level, so this one, okay, this one is Q, I am just assuming. Okay, this is my quantization values. So that means that, so I am taking the mid value mid value is some sort of a 0, this side q by 2, this side minus q by 2. Okay, so that means, say, this is my 0 value, this is q by 2 to minus q by 2. If your range, if you're actually at the sampling instant, if your signal value it is between 0 to 0, minus q by 2 to plus q by 2, then I will just map it to this level. Okay, so sorry. So rather it is opposite. So I will, these are my discrete levels, these are my quantized values. These are my quantized values. Means I will say these levels, these red lines are basically, sorry, these red lines are basically, these are the red lines. I have taken it in this way. Okay. So that means if I have a minus V peak at the sampling instance, I will put it here. If I have plus V peak, I will put it here. Okay. So I will just take it little down. Okay. Now, that if it is 0 plus something, I will put it to the q by 2. If it is 0 minus something. So in this, so is it clear? Now, if you see, that is what is the error variance? That is what can be the error? That is, it is minus q by 2 to plus q by 2. That is E is the error and probability. This is the variance, and I am assuming there error is 0 mean. Now, this probability of error, I am assuming this is an uniform probability, which is 1 by q. Because if you just consider this one, that means this is minus q by 2 to plus q by 2. That means it can be anywhere, and I have the uniform distribution. I am assuming for my analysis, so that I will finally, what is my variance? Variance will be my q square by 12. Now that is very average quantization. Please try to understand this. Variance is like average. Average means that some sort of a mean kind of thing. Average quantization noise power. That means E square is some sort of a noise power, and the sigma square is, that is, you are doing an average of E square. That's why doing all this expectation of E square. So that's why it is average quantization noise power. And what is my peak? Peak is VPP by 2 square. Now VPP by 2 means, what is my VPP by 2? VPP by 2 means at one side is how much? I have L into Q by 2. L Q by 2. So that L square Q square by 4. And what is my, and many times this is the peak signal power. Please try to understand. Because this is my peak signal power and this is the average noise power, average quantization noise power. Now what is my signal to quantization noise ratio? That is signal power, okay, divided by noise power. Now that it is, please try to understand, it is a peak signal power, ratio of peak signal power. 2 means the signal to noise ratio for signal to noise point. Sometimes we say PSNR, please try to understand. Sometimes we say PS, peak signal to quantization noise power ratio or something. Okay, PSQN. That means peak, because it is signal power at peak signal power. Noise is noise power. Peak signal, it is a quantization noise. No other noise I am talking about. Say all other noise is 0 I am assuming, and R for ratio. So peak signal to quantization noise ratio is, if you just do the calculation, there it is 3L square. That means, and what do you want? You want always this ratio should be very good actually. So that means in order to make this ratio big, your L should be big. L big means what? L levels means number of levels should be high. Now so here I have L equal to 4 different levels. So I have used 2-bit ADC. When L is high, that means if you have L equal to 8, then you need a 3-bit ADC. If you need L equal to 1024, then it is 10-bit ADC. Higher bit ADC means actually that means higher resolution ADC means your noise signal to noise ratio, signal to peak signal to quantization noise ratio that will be higher, and your quantization noise power is low. Also ADC will be costly. That is another point. Your ADC will be costly. So, but anyway, if you want better signal to peak signal to quantization noise ratio, you have to be a little. You have to buy the costly ADC, and also your signal quality will be better. Otherwise, what will happen? That means if you have some sort of a say I have a sinusoid like this, and if you choose 2-bit ADC, then and say say it is like this, then you have a blocky type of this type of blocky type of waveform that you don't want. That's why people go for higher order. So finally, what we have got, that means when your that peak signal to quantization noise ratio is 3 into L square. L means number of quantization level. Now let us come to that pulse code modulation. That in the last class we started discussing it. That means pulse code modulation is that I have a baseband signal. That means say I have this type of continuous time signal. Okay, this type of continuous time signal that. Yeah. Now I have sampled at this point. Now sampling, the natural sample value is 1.3, 3.6, 2.3. But I have to quantize the sample because that is, say I have a 1.5, 3.6 is 3.5, like that. 2.3 is. So what are the L quantization level? Quantization level 1, 2, 3, 4, 5, 6, 7, 8 quantization level. Okay. Now that means L equal to 8. Okay. Here L equal to 8. That means say 0 to 7 something code number. Okay. Now that means 1.5. That means 1.5 level is first one is some sort of a, that means what I have sampled, I will just move it to this position. This one. Then this is actually 3.5 or 3.6 and 3.5. Then this one is 2.5. 2.5 means basically I have moved a bit. Then the next one is 0.5. 0.5 is I have down little. And the previous one is minus 0.5. It means I have little up. Actual value is minus 0.7. In that way, now I have a code number. That means minus. Say I have chosen minus 3.5 is 0 and minus 2.5 in that way. So some number it is 0. You can choose it in a different way also. But generally we will choose in that. So this is my code number. Now this code number, what I will do, that means this first one is 1.5. So this code number is 5. 5 I will represent as, say, as I have some 8 different code numbers. So I can represent it by 3 bits. So what I will do, 5 is 101. Now 7, next one is 7. 7 I will send 111. So that means you try to understand that actual natural value at sampling instant was 1.3, 3.6, 2.3, but I cannot transfer that. I have quantized it to 1.5, 3.5, 2.5, but I am not transferring this information. I am encoding it. Please try to understand. I am encoding it. Just let us go to the previous one. I am encoding it. Okay. So is it clear? That means after quantization, I am just encoding these blocks of 1 0 0 1 1 0 in this way. So I am basically transmitting. So please try to understand. This is PCM sequence. Please remember there are two things. One is PCM waveform, another is the PCM sequence. So basically I am representing 1.3 by 101, 3.6 by 111 like this, and I am trying to transfer these bit streams. Okay. Now these bit streams, how will I transfer these bit streams? That I will say I have something like that. See, now these bit streams, what I am saying, no, these bit streams, though it is coming from 3 bits, but no, I will not do. I will take some sort of a 1 bit group together kind of thing. But I will take 2 bits group together. In that way I will transfer. I need not do all 3 bits group together business. Okay. Say I will make 1 as say 2.5 volt positive, and 0 I will make minus 12 volt positive. In that way I will transfer. So that means what I will do, that is my PCM waveform. Try to understand. So that means this is my 101 111. Let me come to it. Let me say this is my PCM sequence. So what is my PCM sequence? Please note it down: 101 111 110, something like that. So let us. I will not discuss this one. Then I will come later. Now that sequence you see, that actually if you can remember it, it is the same sequence 1 0 1 1. Now what I am doing, I am saying no, I will this is my PCM sequence. Please try to understand. Please, this is very important. This is PCM sequence, and I have some sort of a pulse representation. Say I am this one says I am taking some capital T time width. 1 means some voltage, 0 means nothing, and when I have 1, then I will have. So this is some sort of a pulse type representation of this one. Okay. Now this is the pulse representation of PCM. Please try to understand. This is pulse representation. Now, but please try to understand. This is just representation. This is. But what I am doing for the electrical waveform, what I am saying that no, I will do something like this. 1 means some plus 5 volt or plus 3.3 volt I will make like this, and if it is 0 I will do minus something 2.5 volt, and it depends on you, and in that way I will move. Please try to understand, when I am transmitting this information, actually my basic thing was 3 bits grouped together. If you remember, that first one was 101, but I am just breaking that boundary. I don't know, I am just considering one bit, and I am transmitting. So this is each bit duration is each bit corresponding to voltage corresponding to each bit duration is T, and this is T to T in this way. This is called, please try to understand, this is pulse waveform transition between. So that means you see the bit, this is my bit PCM sequence, this is the PCM representation pulse, this is the PCM waveform. Okay, or pulse waveform, whatever it is. Now now the question is that you are saying, okay, I will do 1 by plus 5 volt or plus 2.5 volt and 0 by minus 2.5 volt. Yes, this is fine. But somebody else may say, no, I will represent it in a different way and see, and also I will reconstruct it also this way. I don't have any problem in that case. So there are different methods. So how will you do this? How do you say that is from bit sequence, a PCM sequence, to this waveform representation? Okay, so these are the conventions. Okay, forget about this term, some sort of a non-return to zero, phase encoded. So these are, forget about this one. Okay, there are some methods. Okay, let us see one by one. Some sort of one. There are some, you see that non-return to zero, some NRZ. I only see NRZ. These three are some sort of a NRZ. Then there is something return to 0. I will come to it. What return to 0, what not return to 0. So I have some return to 0. Okay. Then I have some phase encoded. This is some sort of a phase. Okay, because this is phase. Okay. And there are some multi-level binary and all these things. So multi-level binary means, say, this is also some sort of a phase kind of thing, but these are the multi-level binary. Okay, why the multi-level? Because you see, this is one level, this is one level, this is one level, not the two levels binary. But previous to this one, all are two level binaries. If you notice carefully, so here it is, here again it is a multi-level binary. Okay. But anyway, let us see. Let's forget about all this detail. Let us see the representation. What is basic representation? NRZ means non-return to 0. So that means, try to understand, non-return to 0 means it will never come to 0. Now, whatever may be the bit sequence, my state, this signal waveform. See, this is the actual electrical signal waveform. That is V and minus V. This is duration is T. Actually, and that this is my 0 volt. Say I have. Yeah, this is T. Okay. You see, that means when it is a steady state, then only during transition it may cross 0. But during normal state, it will never go to 0. It will not return to 0. So 1 means it will be at some plus V. Now again 0 means it will go to the next minus 2.5. Again 1, that means it is plus, then again plus, then triple 0, then again it will go. So it is not at steady state, some 0 or 1. So neither of these things is represented by some 0 volt. That's why it's called non-return to 0. Okay. Now, so similarly, I have non-return to 0 level, non-return to 0 M for mark, and non-return to 0 L, M, S. L for level, M for mark, and S for space. Okay. So similarly, try to understand that what is mark and what is space. Okay. So if you with NRZ-M, the mark is 1 actually is represented by a change in level, and 0 means it is space. Okay, is represented by no change in level. Okay, if you read this thing, actually it is written in the book actually. That means you will find that different representations. So my basic point is that means I will represent this PCM sequence. This is my PCM sequence. Okay. Okay, this is PCM sequence by different voltage waveforms, different types of voltage waveforms. Okay. So and these waveforms, next class I will discuss this thing. These waveforms will be transferred through the channel. Channel means maybe the baseband wide channel. Okay. And say this capital T equal to 1 millisecond. If capital T is 1 millisecond means what is your bit rate? Your bit rate is then how many bits you will transmit in 1 second? 1000 different. See, if you just all 10 10 10 like that, alternating 10, then you can do this type of 1000 things in a second. That means you are transmitting 1000 bits. So your bit rate is 1 kilobit per second. Okay, for PCM sequence with NRZ-L. Okay. If there is a NRZ-M, M means mark means 1. When there is a 1, say I am assuming I have started from here. When there is a 1, I will just either I start from here or here, it doesn't matter. So I will at 1 I will have always a transition. That means say I have started from here, I have seen 1, I have done a transition. Okay, and I will stay there. Then I have got 0, that means I will not do transition, I will stay at my present state. Okay, when I have got 1, oh, I will do the transition here. Okay, and I will go to that state, stay at that state. Then again 1, that means I will do the transition and stay at the state like this, in this way. Oh, 0 means I will not do the transition. Oh, 1, I will do the transition. Okay, and stay the state. Again 1, I will do the transition. Okay, so this is the NRZ-M. For mark means when you find 1, you will do the transition from the previous state, and you will be staying in that state. Okay. Now, what is my NRZ-S? NRZ-S is when there is a 0, then I will do the transition. At 1, I will not do anything. That means, say I am at, say initially I am at this state. When there is a 0, I will do the transitions. Stay there. At 1, I will not do anything. Again, 0 means I will do the 10th state. Similarly, 0 again transition. This one. Then again 0 means I will do the transition. In that way, I will move like this. So these are my NRZ-L to MS like this. Okay. So there is some problem here. Okay. That means if there is some mistake, then from next point your signal waveform will be always important of what it should be. Okay, please try to understand this last sentence. If there is a mistake somewhere, one transition mistake, then again at the two means when it will commit 2 mistakes, then everything will be taken care. Otherwise, if it is an odd number of mistakes, always your signal waveform will be means opposite from the what it should be. Okay. So now, so this is about NRZ non-return to 0. You see, it is never be at 0 voltage. It will never be at 0 voltage. It is never be at 0 voltage. Now, but unipolar means unipolar return to 0. That means I have only 0 to V. Bipolar means minus V2. Okay, bipolar means both sides of the 0. Unipolar means only one side of the 0. Now, 1 I am representing in, say, this way. I am representing 1 in this way and 0 now. Again, after 0, say 1 has come in, so I have started 1 in this way. So, what I will do that. This is my 1. Again 1. Okay, I will again 1. So, that means this is my 1. That means from top to at the half point, I will do the transition and I will. And 0 means I will not do anything, I will stay in my state. Again 1 means I will go to the top and do the transition and come to the bottom. 1 means again go to the top and do the transition. 0 means I will not do anything. So this is my unipolar RJ. And bipolar RJ, if there's a 1, so I have a transition, but what I will do, the bipolar and also try to understand that return to 0. Return to 0 means, you see, I will always return to 0 at the end. That means from here 1 to, I will return to 0 somewhere here. Again 0 means I will stay at that 0. So that means at the end of the state, at this end of this big duration, so that means that at this bit duration, so it will always be at 0, whatever may be the state. You see that it is at the end of the duration, it will be always at 0. Now bipolar RZ means, say, I have to check it, means 1 means something like that, most probably turn to 0. This is 0 means so bipolar RZ means bipolar RZ. Return to 0 means I have to always see at the end of this one I have to return to 0. You see, everywhere I will be 0. Whatever may be my this thing. This is my end, and again this is my end, and all my all at 0. So that means it is returned to 0. Bipolar means, say, previous case in 1 I have done a transition from top to bottom or top to 0, but here that here for 0 bit also I will do another transition from negative to 0. That means from 1 I will do plus B to 0, and for means logical 0 sequence I will do from negative to 0. From top I will top to 0 for 1 means top to 0. For 0 I will do bottom to 0. In this way, actually I can represent, and there are some advantages and disadvantages of each thing. Okay, so these waveforms are different PCM waveforms. Okay, mainly to transmit the baseband signal. Okay, mainly to transmit all kbps level some baseband line. You want to transmit some WAD telephone channel and all this. So there you want to use this type of waveform. Sometimes we say this is called line code. Okay. Anyway, so that is basically line code, means telephone line code. Okay, thank you. So we will again meet on Monday.